In the last set of videos in this module, we mentioned the word constraints, and constraints are very, very important for databases, especially the relational database model. So I'm going to walk through now a set of constraints that we have and we have to place in the relational model to make it work out for us. So constraints are just that. They are restrictions on the actual values in a database. So it's like this little person here who is connecting things together and holding them together based on the constraints that are applied. So it's derived from rules in the mini world. In other words, the knowledge that the database has and the database represents. A legal state in the database is one that obeys all of the constraints that are there. So there are several types of constraints that we need to be aware of. There are constraints that are just inherent based on the model itself. So it's imposed by virtue of using the relational model. Then we have to follow certain rules, because if we don't follow those rules, it would not be the relational model. The second are constraints based on the schema. We can express those and define those in the database. And then finally, application-based constraints that cannot be expressed or defined in the database, but we can express and enforce them through application programs that we write that use the data that comes from the database. So a few inherent model-based constraints to begin with. First is entity integrity. Every row in a table must be uniquely identifiable. And the reason for this is we have to be able to find a row in the database, and the only way to find that row is to ensure that that row is uniquely identifiable. So what we use to do that is a set of keys. A super key is an attribute or a set of attributes that uniquely identifies a particular row. So that means that if we have a set of values within a particular row, then that set of values will be unique for all rows in that particular relation. A candidate key is a super key that has the smallest number of attributes possible, but it still maintains uniqueness. So there might be super keys that allow us to uniquely identify the relation itself or the row within that relation, but we want to choose a key that is something small, and it's the smallest possible number of attributes, but we still have uniqueness maintained. The primary key is the candidate key that is chosen to uniquely identify the tuples. So no attribute of a primary key can have a null value, because if you allow null values in one attribute of the primary key, it was not needed to maintain uniqueness. So let's take a look at this in an example here. We have a candidate key called roll number, and we have a candidate key called registration number. Those two are candidate keys because we see that roll number is unique across all records within this within this table, and registration number also is unique across all rows within this relation or table. The one that we choose is the primary key. We might choose roll number because that's a simpler number to have. Registration number might be a little more complex. The second type of model-based constraint that we need to talk about is referential integrity. If a row references another table, it has to reference something that exists. So this is implemented in the relational model as a foreign key. A foreign key is an attribute or set of attributes that it's not the primary key of the relation, but it is the primary key of some relation, usually a different relation. So it represents a connection logically between the relation. And this is what I was talking about in a previous video when I mentioned VLOOKUP, because in Excel, this is exactly what we're doing. We're looking up a key based on a foreign key relationship. So we have to know how to look up something within another table, and to do that we are connecting it through a set of attributes that represent that other table. Usually it's the primary key of a relation of another table. Sometimes it can be of the same table, but it's usually a different one. So if a foreign key exists within a relation or a table, then either the foreign key value has to match the primary key value of some other table, or the foreign key value must be completely null. So you can have null foreign keys, and that just indicates that the relationship between the row in this table and the row in the foreign table, or the table that's being referenced, just doesn't exist. If a relationship doesn't exist, then it would be null. So let's look at a more concrete example of this. Notice that the primary table is a list of companies that has a company ID and a company name. In the related table, we know that we have an associated record with company ID 1 pointing to company ID 1 here. It's referencing Apple. So if in this case the referenced value Apple is associated. However, if we look at company ID 15, it's pointing to something that does not exist in the primary table. This is a failure of referential integrity. Therefore, one of the things that we would see here is an orphaned record. This record has no parent. So there's nothing that it's pointing to into the primary table 15. And the relational database model has several ways of dealing with that and how to ensure that those things don't happen, and we do not have a lot of orphaned records out there. Looking now at schema-based constraints, we have something called domain integrity. Domain integrity says that every attribute has a set of restrictions that prevent it from holding invalid values. And the easiest way to ensure domain integrity is the use of built-in data types. The use of built-in data types allows us to say, okay, this particular value is an integer, this particular value is a decimal, or this one is a date, or this one is a string, or a set of characters. So looking at an example here, we see that we have an employee ID, that's a set of integers it looks like, name is a string, salary should be a set of numbers, and then age also should be a set of numbers. But if we notice, we have a violation of domain integrity for employee number 3. It's not an integer, so it's not acceptable. If we tried to enter this in the database, the database would have errors, or would show us errors because it would fail the domain integrity check. And that's a good thing because it protects us and it protects the data that we have. Another schema-based constraint would be considered general constraints. And those vary, but typically they're more detailed than simple data type constraints. So let's take a look at an example of that, where we have the column name, the data type. So this is the domain of order ID. But there are other constraints that we have to put on it. Unique positive integer values, it's an identity that starts at 1 and increments by 1. It's the primary key. So that also enforces the entity integrity, and it's not null, which also, again, enforces entity integrity. The order date is a small date time, so that means that it's probably just the month, day, and year. And it's not null. That's another constraint, a general constraint that we put on this that says the order date must be present in the database. Actual delivery date is another small date time, but we have to check to make sure that the actual delivery date is later than the order date, which should make sense. Order comments, that's a character field of 100 length. The deposit amount, it's some kind of monetary value. It has positive values. The default value for that is 0. And we need to check that the deposit amount is greater than or equal to 0. And then the customer ID is a foreign key that's an integer. It's not null, and the foreign key references the customer ID in the customer table. And it says cascade updates. Cascading just means that if we update this value here, then, or if we update the value in the customer table, then this value would also change automatically. So those are the basic types of constraints that we need to worry about in the relational model.